or with the most complicated logic. And then everything else is like just.
So you guys got the email that we have gonna have a quiz today, right? On tools complement. You guys learned it in logic. Here's a slightly different because we have to implement it onto IPGA. I'm gonna go through the fundamentals of tools complement and how to implement it on your IPGA board for a adder and subtractor, a 3-bit adder and subtractor. And there will be a quiz. I think after the lecture, I'm going to teach it first. I know I'm not expecting everyone to remember everything from logic, right? So I'm going to teach it first, and I'll give you about 5 to 10, probably 10 minutes to practice on it by yourself. You can look at the numbers and do the calculations and try by yourself. I'm going to give you the quiz. It's a 15-minute quiz. I think 5 problems, 10 points for each, so it's 50 points. Is that fair? So after the lecture, I'll give you 10 minutes to collect your notes, do practice, and then do the quiz. Okay? You don't need 10 minutes? 5 minutes? 2 minutes? 3 minutes? Yeah. All right, 10 minutes. So still remember one's complement? These are very likely to be on the interview if you are doing a digital design interview, job interview. What is one's complement? Yeah, it's inverting, just flip all the bits, right? If you have 0, 1, 1, this is 3 in decimal. So for this one's complement, just flip every single bit. So you are getting a -3 for 1, 0, 0, I think, right? But for two's complement, so we flip it and also add a 1 to it. So for 0, 1, 1, it becomes 1, 0, 0 and plus 1, right? So it's eventually 1, 0, 1. So you can always use this toggling every single bit and add a 1 to it to find out the negative counterpart of the number. Okay? But however, it can be time consuming if the number is getting slightly bigger, for example, 4, 5, 6 bits. And there's another way to calculate the two's complement or the negative number, the negative counterpart of it easier, that's how I taught it in logic, right? You still remember how to do it? For example, I give you a number like this. Could you tell what this number is in two's complement? Is that a positive number or negative number first? It's a negative number, okay? So what's the value of it? What's the way to do it? Pay attention because there will be something on the quiz will be highly relevant to this type of calculation. Yeah, so all these numbers are positive numbers, right? But only this guy is a negative number. That's called calculated. You know what I mean? So you treat these ones MSB as a negative number of that digit, then you add it to the rest. That's an easier and better way to calculate the two's complement battery numbers value. Did you get that? So what is this number? If this is unsigned, if this is an unsigned number, okay? So what that number is? 2 to the 4th, right? 16. So in here, it becomes, yeah, -16. So what are these? 7, right? You won't pass any interview if you're still doing this kind of slow calculation, right? So it's going to be -16 plus 7, which is -9, right? So this is -9 in two's complement. Okay, but if you want to use this method, which is adding a 1 and flipping every bit and add a 1, so you have to calculate back. So you have to -1 and then flip. Okay, reverse it to find out the value, the positive value of it, and then add a negative sign in front of it. That takes more time, apparently. So that's why we prefer that you just treat the MSB as a negative number and add it to the rest. Okay? Important, all right? for this. And for today's lab, we are designing a hardware to implement that calculation. So we can do it on the paper, but if you implement it on Verilog and makes it to work with your IPGA board, we have to take care of something else as well at the same time. So first, you have to deal with things called overflow. It's a certain concept, has to meet these two criteria, which is the first one is has to be a positive number plus a positive number, and then you are getting a negative number, or negative plus negative, you are getting a positive number. So only these two situations should be counted as overflow for two's complement. If you are getting carry out, the C2 carry out eventually, but these two numbers are either Pn or Np, even you got to carry out, it's not overflow. So overflow is just a criteria that meets these two situations. Okay, keep in mind. So for example, if we have 0, 0, 1, 1 plus 0, 1, 1, okay. Let me draw the structure or architecture of the adder first. We have done this for a few times. So you'll know what are these, what the carries, the name of the carries. I just named it C minus 1 because it's not anything in here yet. So that's the carry C0, that's C1, and the C2. Okay, this is S2, S1, S0. As a flatter, flatter. These are A0, B0, A1, B1, A2, B2. Okay, so it's like these three, the two, 3-bit binary numbers are being added together. There's no carry in, there's no C minus 1 for these two numbers. We're not using C minus 1 for now, okay? It's just 0. So if you have 1 plus 1 equals 0, right? So there will be a carry. So what's the name of the carry here in this architecture? C0, right? This guy. And 1 plus 1 plus 1, we are getting 1, 1, right? So what is this carry? C1. And then 0 plus 0 plus 1, we are getting 1, right? So what is C2 here? C2 is 0. And we are getting like a positive number plus a positive number because they are I minus P's are all zeros, right? So it's P plus P, you are getting an N here. So for N means we're only looking at the S2. If S2 is 1, we, at this state, we consider this as a negative number. So positive number plus positive number is not, it's impossible to get a negative number. This is wrong. The reason that this is wrong is because we're using two's complement. Two's complement is not a real numbers. They're not real numbers being added together. We have to manipulate it to let the computer understand it, you know what I mean? So it's because two's complement here, if you put a number here, for example, 101, the three numbers, the 3-bit two binary number, the 3-bit binary number like 101, okay, it should be 5, right? It should be 5. Because we can tell the computer, don't treat it as 5. Treat it as -3, right? Is that -3? Treat it as -3 instead of 5. So it is wrong, right? It's not the actual number, but we just tell the computer to do it. So that's why when you are doing all these operations, there will be some errors you have to deal with. I mean, we just need to tell the computer when the error happens and what we do with it. So today's lab is actually you are telling your logic circuits to do whatever is the correct, to get the correct number into its complement instead of just using the adding operation here. So for this example, C2, if this happens, ppn, we're getting ppn, so overflow happens. Then what we do is we want to adopt C2. So C2 now is usable. We can use it. So C2 is 0, right? So we can use it. So when overflow happens, adopt C2. Keep in mind. Are we getting a correct result after adopting C2 here? So it's 3 plus 3, we're getting 6. Okay, so it's legit. This is good. If you have example like this, 1, 1, 1 plus 1, 0, 1, this is negative number plus a negative number, and let's see what are we getting here. So 1 plus 1, what does this carry? C0, right? Okay. C1, right? And this is 1, 1. So C2 becomes what? C2 becomes 1 here, right? So it's n, right? So is there overflow or no? No overflow, because overflow has to be ppn or nnp. So n, there's no overflow. Even though there's a carry out, but there's no overflow. The overflow is just a certain definition we're talking about. Okay? Keep in mind, no overflow. Even though we have a carry out, but no overflow because it's not falling into one of these two categories. So it's called, there's no overflow happening. And the strategy here is to reuse S2 as your MSB. So reuse S2 as C2 for this situation. Remember these two rules, okay? Overflow, then adopt C2. Are you going to be sure about what C2 is from this architecture? Is that going to be a certain number or is changeable? I mean, are you getting if you have A2, A1, A0 being added to B1, B2, B2, B1, B0, the two numbers being added together, okay? Are you getting a certain C2 or it's changeable? It's a certain C2. So because these are computational logic, right? So you will get a certain C2 here. So in that case, if you want to adopt it, you have a C2 value 0 available for you to use. Okay, so if you don't have any overflow, do you have a certain S2 here for to use? Yes, S2 will be generated by the MSB of the adder here, so you can directly use S2 and reuse it for your C2. Which is used and put into the MSB position.
Is it just because S2 will always be the same as C2 if there's not a
No, there are so many other situations I'm going to talk about. I'll give you more examples, and eventually you'll find out that's the correct way to do it to get the right results. And the reason I want to do that is we're not dealing with a complicated like algorithm. We cannot program in the top level programming language like C++ or Python. Okay, you cannot do it by whatever you want. It's a hardware. You have to manipulate the bits by yourself. So when S2 is available, you have to always think about the hardware, the very bottom level hardware, instead of programming on the keyboard. You can do whatever on the keyboard. We'll program with C++ or Python, right? But now we're dealing with a very bottom level. Whenever your C++ program is getting compiled and eventually, converted into machine code, what the computer is going to do, right? We are dealing with that layer right now. Okay. So for two's complement and on the IPGA level, this is very easy to do in Verilog because you can use a concatenation, right? So we can always form a 4-bit number as a result. Let's call it as, okay, or sum, whatever, as the final result. So you can use as2, as1, as0 as the first 3 bits, the lower 3 bits. And now it depends on if you have an overflow or not. You can change this one either to C2 or S2 to output the final result to your anywhere. It can be the 7-segment display or the LED to display the lights. Mm-hmm.
Because the 1-bit adder for the most significant bit would have a carry out.
Mm-hmm. Depends on if you have a overflow or not, I think. So you have to put everything into a truth table and find out all the situations, and then eventually get a logic circuit out of it. So now what's happening is we have to know if there's an overflow or not, okay? And if there is, we do this. If there's not, we do this. But there will be more examples to show you guys, and you will see there are different situations.
So is it like with a negative number, you get and then, so if you're like negative, 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 and then you put a 0 on the front, it's not negative anymore. But if you put 1 on the front, it doesn't like actually change the value. But then for a positive number, it's the opposite. You have to add it with zeros to make it not change the number.
It may cover some of the cases.
Okay. Not fully.
Not fully, okay. Probably. And you will likely, this is still a simple problem. Whenever it scales up, you can miss cases easily. Mm-hmm. So it's better to put all the things into a truth table and find the logic. Or just use it. Just put it here. Just put it here. Yeah, yeah. And you'll see more examples, and we'll find out this is eventually actually solving the problem. So I got more examples here. If we have 111, 001, for example, NP, definitely we know there's no overflow because it's not PPN or NP, right? It's NP something. And this is C0 and C0, C1, right? And C2. Overflow or not? No. What should you do? Do you want to use C2 here? Then it's an error. It's not the correct answer. So what's the first number here? What's the value of it? Yeah, it's -1, right? No, I mean, yeah, this is -1. What about this? It's 1. So -1 plus 1 will be 0, right? So in that case, there's no overflow. So you don't want to use C2. Do not adopt C2 because there's no overflow. So following the rules here, like I told you guys, follow the rules. If there's overflow, then adopt C2. If there's no overflow, put S2 as an MSB, right? Yeah, just put 0 here. So you're getting a correct result as a 4-bit. Yes. Yeah. So you are thinking about why we have to reuse it, right? Because a 4-bit, it's a 3-bit adder, and you are getting a 4-bit result. You have to put something at the MSB. So it's actually a very good question. So why putting or duplicating or replicating the existing MSB in front of it, or keep replicating that digit in front of it is not changing the value of the two's complement. No, try it. 101 is what? So -4 plus 1, right? Let's put 1 in front of it, like 1101. Just adding a 1 to it. What is that number? So -8, right? 5. It's not changing it. What about this?
So why is that not just like the universal rule?
What do you mean by universal rule?
Maybe I didn't say it right, but that's what I was talking about before. Was like when the MSP is 1, it's negative, so you keep padding it with 1, the lab so it doesn't change the value.
Mm-hmm.
But when it's 0, you have to pad it with 0 so it doesn't change the value.
Mm-hmm.
So that's why you have to do it like this, or there's other cases.
Yeah, it covers most of the reasons. I think you want to do that because it's not changing the value, and also for the 3-bit adder, you have 4 bits as the result, so you have to put something in there, right? So always think about the hardware because no one is going to do that for you. It doesn't like a higher level programming language. No one's going to do that for you. You have to, comment every single bit. You have to know what you really want at that position of the register. So this one, you got it? The reason we are putting S2 here is because we need that bit for the MSB, for the adder, right? Okay. Yeah. So use this one, right? Concatenation to form the result. Yeah, that's Verilog, right? No overflow, you put S2 here. Overflow, you put C2 here. Yeah. Are you ready for the quiz on this? So one thing, okay, one thing. I'm not done yet, but very soon. Okay, so first, overflow, adopt C2. No overflow, S2. Okay. That's called the strategy to implement this tools complement adding in your Verilog. And here, if we keep adding ones in front of it, are we changing the value of it? No. So what is this number in? Rick, do we have this number in tools complement? We do, right? Is that -1? Yeah.
Also, you invert
You plus and invert, right? 0 and yeah, it should be -1. Okay. So if you add 0 in front of, are we changing it? Yeah. Okay. All right, and so if you want to reduce the complexity of a number, you could either adding 1 in front of it, probably not adding, but you can reduce ones in front of it, right? Okay. So now another remaining issue here is because we are designing the hardware, right? And we can find out if there's overflow or not by looking at this. So our brain can resolve it. But what about the hardware? How do we tell? How could the gates tell if there's overflow or not? Because you are either think about the if statement in Verilog, right? So if overflow, do this. If no overflow, do this, right? So you'll find out. I'm going to draw the truth table. So this is another example I want to show. That's why I want to give a lecture in front of it because I mean there's a certain way to do it. This is more complicated than that. I think if you look at the truth table, a few bits are getting involved. If you see here, a few bits are getting involved. I think these two are getting involved because these two numbers will determine what the S2 is. This one also determines it as well. So I think it's going to be the 4 bits here to determine if you should, if you are going to have overflow or not. So it's only 4 bits. Okay. If you put in truth table, there will be how many entries?
You would need S2, not C2.
S2 is determined by these two numbers, right? No, S2 is determined by these 3 numbers.
Yeah.
Okay. So in terms of C2, why do we need a C2? Yeah, yeah. Because these two, so these two has to be either the same, has to be the same, right? The same sign. Okay. So that's why these two has to be involved, and this one will be added to these 2 numbers and giving you C2 to determine if it's. Do we need the C2?
It seems like you can't use S2 because you add them, check it, see if it overflowed. If it overflowed, then you use C2. But you can add them without any. You could just do it with V2A. Yeah, you could, but it would be more complicated. V2, if they're all in S2, and you compare V2 and A2 to S2. Why not just
and then B2 and A2 are the same sign, opposite sign to S2, then you know that's over.
Yeah, exactly. Yeah, that's what.
You don't need C1 or C2.
But you would still need C1 to get S2. So in that sense, it would be involved.
That's right.
So you would just, yeah.
So if you look at these,
add the 3 together, check A1 or A2, S2, and compare them.
So we do need a A2, B2, C1 for sure, right?
Yes.
But do we need a C2 or not? The conclusion is yes, based on all the previous experience, but I couldn't tell why right now. No, we are determining if we have overflow or not.
Yeah.
Then we try to say if we want to use it or not.
Could you just write it like,
Let me see. I'm pretty tired right now, but so do we need a C2?
You could sort of make it more direct by like adding it with the expression of if there's overflow or not. You just get the bit.
So B2 is not really making a change, right? If we have A2, C2 here and C1, then we will know what this number is. But do we really know if this is opposite to these 2 numbers? Probably. Since we add them together, so you have to, if you don't use C2, then you have to add them together and then check if they are opposite or not, right? Yeah, so you have to do that extra step. But if you have C2 involved, you could tell, right? So C2 has to be involved, otherwise you have to do another step, one extra step to check it, right? So let's get C2 involved as well. So we are trying to find out the overflow bit. So the overflow bit will be either 1 or 0. 1 will be overflow, 0 will be no overflow. Okay, so we can definitely check that number there in Verilog. So if, right, then do this. So for all the possibilities, we just put all the entries here. It's going to be 16. I'll do that. Okay. So what are the cases? It's giving overflow. This is very easy to tell actually. You could tell definitely. It's just we have enough information here. What about the first one? PP PP will give you a P as a result, right? So definitely it's not going to work. No as well because it's not even the same sign, right? It's NP. So let's just cross out all the NPs. Okay, NP. All right. So NN, you're getting a 0, right? But there's no CL. CL C2 becomes C2 0 here. It's possible because 1 plus 1 definitely you are getting. So 1 plus 1 plus 0 you are getting C2 as a 1. So this case, you got that? Right? A2 B2 C1, right? So specifically A2 B2 C1 are adding together to get a S2 and C2, right? So we're ignoring these numbers for now since they're not involved. Okay, is that clear? So we're only looking at this. A2 plus B2 plus C1 will be S2 and carry out the C2. Okay, so we have all the numbers here, so we can easily tell if it's possible or not. So this becomes A2, B2, C1, and you are getting 1, 0, right? So C2 should be 1, but this C2 is 0, so it's impossible. 0 plus 0 plus 0, C2 got to carry out. Where does that carry out comes from? 1 plus 1 plus 0, you're getting 1, 0, right? It's possible. And it's a n plus n, and you got a p, right? Yeah, so it's overflow, so we put a 1 here, all right? This becomes p plus 1 will be, so no carry out for sure. And two p's are getting you an n because you got a C1 here, right? Are we getting that, everybody? Yeah? Following? Okay. So put a 1 here, overflow, because it's p plus p, you're getting an n. What about this? N plus 1 should be 1, 1, right? But C2 is 0, so it's impossible. 0 plus 1 should give you a 0, 1, right? So C2 is 1, it's impossible. 1 plus 1 plus 1 will be 3, will give you a 1, 1. 1, 1, so 1 of the 1 is result, is S2, so it's n, right? So it's not overflow. So only these two cases. You could put, C1 not and C2 and A2 and B2, or C1, C2 not, A2 not, and B2 not here as the overflow bit. What? A what? How do you simplify it that way? I mean, since these are the two inches on use, right? And these two. But eventually, you are able to simplify it because A2 and B2 really doesn't matter here. What only matters is C2, C1, and C2 has to be different by looking at the truth table. So if you look at, for example, I mean, can we simplify it here from here? Probably not. I don't think so. So this is not 0 volts, right? Overflow. So whenever C1 and C2 are different, you are getting a 1. That's true for these two, but is that true for all the other ones? So could you just use how do we simplify?
I feel like it doesn't make sense to not involve four. Because you need to know what you're adding together to know whether or not you get an overflow.
But how do we implement in hardware, right? You need the logic for hardware.
Isn't that the logic?
It is. You can definitely use this one. Yeah. But I think since we have S2 available, I think eventually this will be simplified. You can, because we don't have S2 involved, there must be a way to simplify these things to S2, because the eventual result is you got C2 XOR S2, I think, for OV overflow. You could either do that or do this, because S2 is a result of C1. Can we use S2 here instead? I think we should use S2 instead of. Yeah, I think we should use S2. Let's try it. Right? But we have C1 here, so we're not tossing C1 in the truth table, so it's okay. Yeah. Shorter, it is only 3 bits. It's okay, I'm paid for salary.
Isn't it A and B mark C? On the top, is it C1 and C2, or is it A2, B2?
A2, B2 is S2. A2, B2, C1 is S2. So we pass A2, B2, but we keep C1 in there and put S2 here.
Okay.
Right? So we can simplify it. Because S2 covers A2, B2, C1. Why keep C1 there? Because we have to look at C1 to calculate C2. Right? No, S2 is independent. It has to be there. Because S2 is connected to the A2 and B2. Let's figure this out. Overflow or not? So it's going to be S2. Oh, is S2 being added to C1 or no? No. Yeah. That's right.
So could you also just do it by comparing A2 and B2 to S2, even though they're wrapped up in it?
Say it again?
Could you also just do it by comparing A2 and B2 to S2, even though they're like wrapped up in it? Just need to check the MSB of each.
If we have S2, why do we still need A2 and B2 though?
To see if it fills that. Like, because if any time they're the same, but the sum doesn't, but S2 doesn't match up with what they are, so you can like not XOR those two, and then you could not handle, I think it would be with S2, and then you just.
Let's do this first, and then we talk about that. Okay. So I'm just wondering if we can get enough information to see if we need overflow or not by doing these two bits. Okay, can we? 0, 0. It's hard to tell, right? Because we don't know A2, B2, have to cover A2, B2 cases, right? So we can look into here. We can use two truth tables at the same time. Go we? So when I think it's just more confusing people more, I think. There must be a better way to teach it. we can do it, right? So when S2 is 0, you can just find out that all the S2 is zeros, right? So only these two cases works, right? As overflow. And S2 is 0. Okay? Because this add to this is 0. Oh, no, you have to consider C1 as well. So this is 0, but this is not. Okay? So if this is 0 and C2 must be 1 to overflow, so there's no overflow here. And then for this case, it's S2 is 1, so it's going to be this entry, right? And C2 is 0, so this one has overflow. But this one doesn't have, wait, but these are not, these don't have overflow. Which truth table you are talking about? Here, in here? Here? C2 is 0, yeah, that's right. I think it's not. I think that was not S2. That was C1. I guess. I probably got the wrong. Remember the wrong schematic. Let's take a look. It's probably C1. Oh, it's C1. It's not S2. So if we, so Mason was right. That was not the. So still have to come back here. Okay, so this one is a good one to do because we know these are all the bits involved, right? So this truth table is legit, no problem on that. So now we want to see if, all right, C1. If we need an A2, B2 or not, because these two definitely showing an XOR logic. When they are different, you are getting a 1, right? No problem on that. Okay, but there are other cases. For example, these two, these three, also shows that C1, C2 are different. If you directly use this logic, C2 XOR C1 to get overflow bit, what about these cases? This is impossible, this won't happen at all. Can this happen? It won't, because 1 plus 0 is going to be, C2 will be 0, so this is also impossible. Right? Same to this. C2, this just won't happen. 1 plus 0 will be, C2 will be 0. That won't happen. So what about these three here? 1 plus 1 plus 1 plus 0 plus 1 will be C2 will be 1. So this is impossible. 1 plus 0 plus 1, C2 will be 1. This is impossible. And this is also impossible. So that's why we can directly use this logic to find out the overflow bit, the control bit. Right? Because these are just impossible. That won't happen. Because of the architecture of the adder. Impossible, we just don't look at it. If that first that won't happen, if that just won't happen. Period. Based on the architecture of the adder, right? It just won't happen. We list in the truth table because we have to list all the entries for the 4 bits. Eventually, if you have 0, 1, so 0 plus 1 plus 0, C2 must be 0, but you are getting a 1 here. The same cases for the other cases, so that won't happen. So in that case, only these two happens, and you want to give overflow a 1 here, and during that 2 cases, C1 and C2 are definitely with the XOR logic. So you are thinking about, what about A2, B2 here? Do you care about that? Why? Because you have other XOR logic somewhere else which has different A2, B2s, and they just never, these are just impossible. Okay, so that's the final logic to get the overflow bit. So you can use the if statement to check that overflow bit to consider place the C2 here or place the S2 here at the final result. And the lab requires you to display final results on the LEDs.
Right, so this is a quick introduction to the lab.
Sorry? If it's a negative number, okay, if it's a negative number, you want to show a bar in front of it, like a negative sign in front of it. How do you know if it's a negative number in hardware? Yeah. If the minus 3 is 1, so you have to get the final result first, right? So get the final result first. Then you check the MSB. If the MSB is 1, then you have to add a bar in front of it. Okay, so just enabling these 2 bits really quickly. Whenever it enables that one, the MSB unit, you just put a bar in there. Yeah, I don't think I explained this really well. I'll rethink about it and then let you guys know later. Okay, I don't think I did a really good job here.
It's a certain way, you know, like if more than C2, it makes sense.
Okay.
Because it's like the only way, if you have C1 and C2 as both 1, then you're gonna need to have like if A and B are different.
Let's don't come.
That makes sense if you write it out. Like all the
Okay. But quiz is not on the truth table there. Quiz is E there.
Yeah.
So the first one is already demonstrated in the IPGA on the IPGA board, and next week's tasks. So I won't have any lectures next week, and you can come over here. Let's do it in my lab. You can either work in 601, 602, or somewhere else, but I will be in my office next week on Thursday. Yeah, is that okay? Yeah. And next week's task will be a serial input instead of the parallel input from the switches. It will be a serial input. You have to pump it in. Yeah, it's going to be a serial input. So you have the three 2-bit numbers, right? I don't know the 2 3-bit numbers, but you have to pump them in using rising edges. Okay, so serial in and parallel out. So you can think about the architecture of it. Have to add. Oh, I missed one thing here as a subtractor, but okay, that's okay. So you can think about the A and B's. They have to be controlled by another layer of D flip-flops on the top of it. So you have serial in, right? So serial in data is coming to the top, and then another clock to load it to the adder and subtractors, so they can do the operation. You need another clock to load it. Okay. So one thing here I didn't talk about is for subtractor, you can simply add an XOR gate here because A XOR 1 will be what? How to find the result for A XOR 1? Because A can only be 0, 1, right? If A is 0, 0 XOR 1 will be 1. If A is 1, then 1 XOR 1 will be 0. So it seems like it's an A bar. So A XOR 1 will be A naught. And A XOR 0 will be A. It did the same way, okay? So in that case, you can flip or toggle all the bits of A, like A2, A1, A0, by XORing every single bit with 1. Because in 2's complement, if you're doing addition, it's easy. Just adders. It's doing addition easily. No problem. So we are doing subtraction. You have to convert it into its 2's complement, which is B2, B1, B0 plus. Right, it's going to be plus because the adders are just adding, it's not subtracting. That's the IFA, it's a full adder, it's not a subtractor. So when you are doing subtraction, you have to add a negative number. Right? So if you want to get the negative number of the A's, follow the 2's complement rule. You flip every single bit and add a 1 to it. Okay? This is how you flip it. Okay? You XOR with the 1, you got a switch. You have to implement that on IPGA. You got an extra switch on the left-hand side. You turn it on, you give a 1 to it. So that 1 will be this 1 here. Yeah, and this one will be put into C in as well. So you are flipping and add a 1 at the same time. So you are converting that number to its complement negative number to do the subtraction, right? Make sense? Okay. So that switch will flip all the bits and add a 1 to the carry in. So you want to connect that switch as one extra switch to the carry in of the entire 3-bit flatter or subtractor. Okay, so one quick question here. So if you want to do subtraction, what's the switch input? So you have already upload everything to the IPGA, and now you are doing addition. You are adding 2 numbers. You want to switch on that little switch controller here, right over here. You turn it on or turn it off to do adding. Yeah, turn it off because you are putting a 0 to it, and you don't want to flip all the A's because then you use the original A's. You don't want to add a sign to it. So A's plus B's will be addition, right? If you want to subtract A's from B's, then you have to switch it on, so which will flip all the bits in A's, and also at the same time adding a 1 to the carry in. So that's 2's complement conversion. All right, that's everything I want to cover today.